I want to do two things today. I want to cover a little bit on databases, just to give you an introduction to it, which is section 8.4. And those are actually posted. And then I want to discuss the final. The final will be worth 200 points, but let me come back to that. I'm going to spend about half the time talking about database and the other half talking about what you might expect on the final. You should have gotten back the S3 homework. I'm working on the S4 now. For those of you that have the 561 exam, well, since some of you may have other exams, if you need to delay the homework till Friday or Saturday, that's okay, because that's probably when I'm going to, at least for those last, particularly the last assignment. And if you can get the next to the last one in prior to that, that would be good. But again, since I've been slow, I'll let you be slow if you have finals and want to finish these like on a Friday, Saturday. But try to get them in. I don't have too much bunched up next week. So try to get them in by Friday or Saturday by the latest. The assignment to the R package, but more importantly, the last assignment on what 4, 5, and 8, I believe, mainly 5. I'll try to give a little bit of feedback on some of these prior to the exam, particularly the S3 and S4 classes. Most of you did pretty well in the S3 classes, and there are several different strategies you could use in doing it. Oh, I thought I had posted the student evaluation instructions, but in my last class, no one seemed to be able to get access to it, so I've got to figure out what the problem is. See, did anyone check their Mix account? Is there an email saying? If there isn't, then I don't know what's going on. I'll have to. I tried to do it last night, and I couldn't even get on the system, and I got on this morning, but it was somehow different, and there was something. It didn't appear that it let me finalize it. So again, I'm sort of looking into this. Hopefully, I can figure out what's going on. In this class, it was going to open today and go till Friday. My other class is a little more problematic because I cut it off sooner because of the final was sooner. So hopefully, I can figure out what's going on with the SEI. So I'll remind you to fill it out, assuming I can figure out what's going on. I know they were having trouble with the SEIs because I had I'm actually chair of the Senate committee on the SEIs, and we had a meeting Friday, and the guy from OIT that was supposed to be there wasn't there because he said he was trying to fix the SEI problem. So I'm not sure what the problem is, but maybe that's what I encountered. So what I'd like to do now is to go into our studio and take a look at databases. This is section 8.4. Again, if you look at the notes here, I posted notes right here that you can download. Unfortunately, I had both of those expanded to full screen and it disconnected. Let me get rid of that one from full screen. Okay. So, what is a relational database and why is it important? Well, if you've got relatively small data sets, you don't need to put it in a relational database. But I've been involved on a number of projects that are fairly big, that have huge amounts of data. And at some point, you need a more efficient way of storing it and a way of retrieving the information. And we do it, if we do it in a structured way, we typically do it with what's called a SQL database. SQL stands for Structured Query Language. It's the way you actually retrieve information from the database. A database consists of a bunch of tables. But the tables are linked to each other, so you can combine tables in various ways. We can do what is called joining. And so they have to have a common key in order to join them, one or more common keys. And that will allow us to do operations that we did in R, such as merge. But in a database, there are similar concepts and similar constructs that we have in R. Particularly the section 9.8 that we talked about from the other book, we talked about things like merging and making data long from wide to long and long to wide and so forth. So there are a lot of operations that you can do in R. Then there are similar operations that you can do in a database. And we're not going to do a lot of them. I'll just I'll go over a couple things today. Now there's a topic, when you learn sort of basic algebra, you learn certain operations and you learn how to do things, and that gets you a certain distance if you're working with functions. But then for a lot of statistics, you get into matrix algebra, which sort of raises the bar a bit. And we have systems of linear equations and some things like that we have to solve for. But there's another important topic called relational algebra. And relational algebra is what is behind relational databases. So these are all topics that students should probably know, and relatively few do. And so these are kind of things that I think should be incorporated in our courses more fully, and that's something that I'll be doing into various, even intro courses that students from various departments take that are not just statistics students. Because increasingly, you're going to access data in online databases. To give you an example, in Bioconductor, information about genes was stored in these what are called annotation files. And not only that, PubMed and all the articles in bioinformatics and biomedicine, etc. There's this huge database of articles and abstracts and linking information of co-authors and citations and all that kind of stuff. They're in databases. But the annotation information in Bioconductor was not in a database. But several years ago, all the annotation information from all the different environments started being moved to databases. So that if you want to get information, bioinformatics information that's been published and available through R, in the future, you're going to have to use databases. It's simple as that. And I'll illustrate a few things today. So increasingly, understanding databases will be essential. Now, when we talk about SQL databases, we have, that's based upon relational algebra. But this is not how Facebook and Google and Apple and Microsoft store their data. Most of their data is stored in NoSQL databases. And again, that's a topic we won't be getting into in this course, but it's a course we'll be designing where we will look at these topics. And so, don't think that it's sort of a question of, in other words, if you're in the business school, you probably think in terms of Excel spreadsheets. And in the business school, they do way too much in Excel spreadsheets. Spreadsheets have their place. It's what's called a reactive programming model. You have a table, let's say, as an example. And you make a change in that table, and that change has a ripple effect depending on the formulas used in that table. And so it's reactive to changes you make, and it's immediate. Now there's a graphical system in R, particularly the RStudio folks, called RStudio, that lets you, in a web page, have a graph with controls that you can change. But when you change them, again, there's a reactive programming model. And there's a client and there's a server. And when you change on the client by dragging a bar, let's say, then it actually sends the information to the server. Server recomputes it and comes back and redraws the graphs. So that's a reactive client-server model. Excel doesn't work that way, although there are spreadsheets, there are some open source spreadsheets that let you operate this way within a client-server environment. So there are spreadsheets that are much more powerful than Excel that you can actually embed R in, and you can do it in a client-server way. So if you kind of keep moving up the ladder here, we typically have data in data sets, these rectangular sort of arrays, except that they're not arrays, because the different columns can have different types. And in R, we call those data frames. And in SAS, we call them data sets. In JMP, we call them data tables, etc. And so that's the organizational form. And we may have multiple data sets that we can use various R operations to merge and so forth. But then as we get bigger, we go to relational databases. And that's where the information is structured. But there are multiple tables, maybe hundreds of tables. And you have various operations that operate on the tables to form new tables that you can then do things with. And now if I move up the scale further to very massive data sets, then I move into things like NoSQL databases. And they may have redundancies in various ways, but they're a very different model for storing things. And they have to be very dynamic. If you look at Facebook, it's constantly changing. And of course, that's a social network model. So we have to think of data in a slightly bigger way. Perhaps the biggest way we think of it is with what's called a Hadoop environment. And that's a distributed database, distributed over many machines, and done in such a way that it's fail-safe. So that if any given machine fails, the whole system doesn't fail. So we're going to focus here on not so much SQL per se, but R interfaces to these environments. And R has interfaces to the common database systems. We're going to be focusing on what's called SQLite. Now, SQLite is like R. It has a platform-independent way of storing things. So that if I store a SQLite database, I can get information. I can move these tables, they're actually files in SQLite, from one platform to another, and it still works. Just like R. You can take your R workspaces and move them from one machine to the other. It still works because it's stored in a platform-independent way. Now, besides SQLite, which is what we'll focus on here, and that's what Bioconductor uses SQLite. So that's part of the reason we'll focus on it. There are two very powerful open source environments, PostgreSQL and MySQL. PostgreSQL is perhaps the more powerful of the two. But again, MySQL and PostgreSQL are both quite powerful. And then, of course, we have Oracle, which is perhaps the biggest commercial system. It's what the university runs on, Oracle. There's also a standard called the ODBC, which is Open Database Connection Standard. Now I'm going to focus on SQLite, as I said. So if I click on this and I'm going to load the library for SQLite, and then I'm going to create a DB driver, database driver for SQLite called M. And then I'm going to form a connection. I'm going to form a connection called con, a database connection using M. Now there's a data set called US arrest. Now there are two ways we interface with databases in Aura. One would be we have databases and we use Aura to extract information, bring it into Aura, and analyze the data. The other way is we have information in Aura and we want to push it up to the databases, which is what we're going to do here. We're going to take, there's a data set called US arrest. So here's the data set. Okay, this is the data set. This is in Aura. I just brought it in with the data command. And I'm going to do a DB write table. And this is actually going to write this into the database. And if it already exists, like if I've already done this, it's going to overwrite it. And so I'm going to write it. I just said DB write table. By the way, I'm using sort of a standard here called a DBI. And DBI allows us a common way of doing things across several other databases, which includes, I believe, SQLite, MySQL, and Oracle. It doesn't yet include PostgreSQL. If I want a list of tables in my database, I only have one, US arrest. So what I did is I had some R data and I pushed it to this database. Now I mentioned the database interconnect, the DBI interface. And this allows me, for example, to do something called database DB send query, which sends a query. Actually, sending a query isn't quite enough. Sending it doesn't actually get it. I have to fetch it once I send it. And so you create what's called a result set. And a result, I can send various queries, but it doesn't actually bring them down to R. Unless I do more, and particularly use the fetch command. And then I can clear the results by db clear result, and I can of course save them. So let me just look at this. So I'm going to send a query and call it RS, and I'm going to say select asterisk. That means the asterisk means select all from the table US arrest. So I'm going to select asterisk. I'm going to select everything. But you notice when I do this at this point doesn't actually bring them into R unless I do fetch. And then once I do fetch and I say n equals 5, it means select the first 5 records, and then here's DB1, and it's selecting the first 5 records. So now I've brought them back down into R using DB send query. And this query, this is actually this part right here is actually a SQL command. It's part of the language. That's the language of, notice it's in quotes because it sends that to the database, and then that's executed on the database using, that's SQL. That's a simple SQL statement. And here I'm asking the question, DB has completed. And the answer is no, it's not completed. I brought down the first 5 observations. And if I do a list results, it's just telling you what, it's telling you using DPI, and it's just giving some internal information on the SQL result. If I want to fetch the rest of it, I can do that. And that would bring down, the -1 means fetch the rest. And then I could ask now, is it completed? And the answer is true. And that shuts the database connection. So what I did here is I first of all took a data set, US arrest, in R, and uploaded it to the database. And then I requeried it back into R. It's a little bit redundant, but it tells you the types of things you can do. And I used a simple SQL statement in order to do that. Now, remember, there was a command, db send query and then fetch. You can combine those together if you say db get query. If you say db get query, it actually not only sends the query, but it actually retrieves it without doing two different R statements. Instead of db send and then fetch, that will do both. Now, this list tables, in this case we only have one table, but typically a database may have lots of tables. So if you say list tables, it will list all the tables in the database. A database typically does not exist, it's not just a single table that's in a database. You have multiple tables typically, and they have common keys that allow you to join them. And we'll talk a little bit about joining in just a few minutes. And if I list the field, this is database list fields. So here are the fields that are in the database. The row names, well, they're right up here where it says D1. The database names, murder, assault, urban population, and rape, those five. Now generally, we can form a query typically using the paste command. In R, you're going to send a query as a character string. So, and typically you say select from something where something is true, and perhaps you order it. You give an order. So in this case, I'm actually giving two strings that I'm going to paste together. The first string says select name from the SQLite master where, and this is going to get joined together, where the type of query is table. I'm trying to query tables ordered by name of the tables. So that actually forms a query. It's a character string. So for example, if I do this and then I look at query, this is actually what gets sent right here. That's what gets sent once it's on the server side. That's the actual query in SQL. And so if I do this on my connection, if I do this and look at fetch it, in this case, it's just the name of the one table. That's all it is, because I only have one table. We're going to look at cases where I have more than one in just a minute. Now, I could do a conditional selection. Select all from US arrest where murder is greater than 10. So you're not really going to, you're going to get all variables or all columns, but you're only going to look at the case where the murder is greater than 10. So I'm going to this same connection, I'm going to send that query and I'm going to fetch it. And these would be all the cases where murder is greater than 10. Do you see what I'm doing? So I said I want all my data to satisfy the condition that murder is greater than 10. You can see that in the column murder, there's a 10.4, but they're all greater than 10. And then I can say database has completed. And in this case, that's the whole thing. So it's completed. I can clear it. And then I can actually unlink test and completely unlink from that. Totally unconnects me. The connection the CON, the connection I have is now gone. And typically you should do that. You should always unlink so you don't leave it hanging. So that's just a few simple things you could do. Now, as I said, as I've already said, that SQLite is very lightweight. It's built into certain operating systems like OS X that runs on these. It's built in. So you have SQLite built into certain operating systems. It has some very advanced features, though. For example, you can store what are called very large binary objects or blobs. You can also create prepared statements. And so it's not a trivial database, but one of the things I like about it is it's platform, just like our platform independent I've mentioned before. Now, there's a database, this Human Genome 95, AV2, it's in a SQL database from the BioInf package. And this maps between the corresponding alphametric chips and quantitative effects of interest in other databases such as Go or PubMed. So I mentioned Go and PubMed, and we talked about that, I think, last time. So what I'm going to do is, again, I'm going to, I guess I don't need to do this, but I'm going to form a new driver. And then what I'm going to do is I'm going to retrieve this database from the package BioInf. And I'm going to form a connection to it. And then I'm going to list the tables in it. So let's take a look at the tables. So these are the different tables in this particular database, this Human Genome 95 AV2, which is a SQLite database from the package. It's from a package, BioInf. And it has ACC, which deals with alphametric data. And then it has several, the next four relate to Go. The EVI is evidence, the ONT is ontology, the ONT name is an extended name for the ontologies, and then the Go probe is the probe information from alphametrics, and then PubMed is this huge database of publications in bioinformatics and biology. A huge number of journals in the medical sciences, in a broad sense of that definition. So for example, if I want to list what the fields are for tab 1 is the ACC. There's the AFI ID and the ACC number. And then for tab 2, which is the evidence, it has the evidence and a description. And for tab 3, that's the ontology. It gives the Go ID and the ontology label. And then for the next one, it gives the ONT and a more complete name. The labels are like BF for biological function. Those are the types of ontologies you can have in the Go database. And the next one is the probe information, the AFI ID, the Go ID, and the evidence. And then finally, the last one is the PubMed, which has the mapping from the AFI ID to the PubMed ID. So this is on some online databases. So the Go ANT maps the Go IDs to the Go ontologies. And the Go ontologies are the BF, MF, biological processes, BP, and MF is molecular function, and CC is cellular. Yeah, let's do some cellular. What's the other C? But at any rate, CC is the other ontology. And then the Go ontology name is a table that has a more descriptive name rather than just BF, MF, and so forth. It has a more descriptive name. So now I'm going to have a SQL statement. I'm going to do a query with a paste. And let's execute that. But that forms a query. So what this says what? It says select Go ontology dot Go ID. That says from the table Go ontology, select the field Go ID. And from the table Go ontology, select ONT. And then there's another one, Go ontology name. From that table, select ontology name. So it's selecting three things from two different tables. There's something, period, something. On the left of the dot or the period is the table name, and on the right is the field name. So, and this is from Go ontology. It's from two different databases. So Go _ ontology and Go ontology name. So notice that I'm selecting three things. This from the Go ontology database table, this from the Go ontology, and this from the Go ontology name. And I'm selecting from this database and from this data. Actually, those are actually tables. And then it says where And this is where we join them. The Go ontology, the Go dot ontology is equal to the Go ontology name. In other words, this has to link the corresponding rows of these two tables that have the same name. So I've done that. So let's do a query. We're going to send to the database, to our connection, the query. I just formed a query. The query is actually, if I now look at Q-E-R-Y, if I now look at the query, it's just a long character string that's going to send to the database to actually get the information. And so if I say rs, I'm going to send the query, and then I'm going to fetch it, and let's look what it got. Okay, well, this is the first three. I said n equals 3, so this is only the first three that it gets. And so it has the Go ontology, it has the Go ID, the ontology is MF, the ontology name is, notice it's longer, molecular function. So it actually returns those three. And those three correspond to this one, and this one. After the select, those are the three columns I get from the two databases, but the two databases had a common key that they were joined on. And that's where the where came in. And now I could say, I could clear the result because I didn't bring them all down. Okay. And so we could do another one. By the way, this is called an inner join. This is an inner join. I'm actually joining from two different tables. And now I could do a select ACC num from GoID from ACC and GoProbe. I didn't use the dot notation there, and usually it can figure it out. From Go ontology and go on. Oh, I'm sorry, I'm down here now. So this is from, I'm selecting these two columns from these two tables, and this is where I'm checking to make sure the ACC AFI ID is equal to GoProbe AFI ID under those conditions. So I'm going to form this query, and then I can pull this information in, and again I'll take a look at it. And those give the ACC numbers corresponding to the Go ID. And then I can clear the results. That is called, both of these results I just did are called an inner these are called an inner join. I'm taking two or more tables, and I'm bringing information together according to common keys. So that's a very common operation. It's sort of like a merge in R. Now, SAS and jump both have similar concepts in terms of merging data from multiple tables. So whether it's R, SAS, or jump, you have a similar type of operation as you have here using the inner join. Now, I think this is sort of the final thing I want to do, or almost the final. I'm going to look at self-joins. Now, a self-join, this query illustrates the first concepts. Notice I have G1 dot star, which means all, G2 dot EVI for evidence. So what is G1 and G2? Well, G1 and G2 are abbreviations. Rather than writing, and this says from GoProbe, and GoProbe is going to have an alias called G1. It's just an abbreviation, so I don't have to write out Go_probe. So G1 is the same as GoProbe. And G2 is the same as GoProbe also. So in other words, I have two aliases for the same data table. Now there's a reason we want to do this, which I'll show you later on why actually we want to do it. So the G1.star is going to bring in all the data, and then G2.evi is just going to bring in the evidence. And then it says where, and this says G1.goID is equal to the specific ID in the Go database. And G2goID is equal to the same thing. And, so this has a whole bunch of ands. This says the G1 AFI ID is equal to the G2 AFI ID. and so all of these conditions have to be satisfied. And G1 evidence equals IDA, but here's the difference. The G1 evidence is IDA, and G2, the evidence is ISS. Those are two different evidence codes. So that's a query. So I'm going to paste that together and then send it to my database. And then I'm going to fetch it. Now notice that I have an AFI ID connected to a Go ID, and the evidence, there are two types. These are all the ones that satisfy both types of evidence. Yes, Steve?
Still not working.
Does anyone check their computer? Still not working.
I called them, but I'll call again.
Okay, thanks.
Sorry about that.
Hopefully, this is going to happen every day this week. But I guess it doesn't matter so much doing too many classes this week. The last thing I want to mention is just a little bit about the annotation database. The annotation database sort of connects information. So, as I mentioned, these annotation databases use this underlying structure called Annobase DBI, or DBI for database interface. And the key concept is what's called a bitmap. Now, a bitmap consists of left objects and right objects. So you can think of a bunch of circles on the left and a bunch of circles on the right, and there are edges between them, or at least between certain objects on the left and certain objects on the right, there's an edge. And so we're trying to relate objects, one set of objects with another set of objects, and the link means there's a relationship between them. In graph theory, this is called a bipartite graph. Now, so basically, the left and right objects, if you can think of them as R objects, so I have R objects here and R object here, the left and right objects can also have attributes. So I have the concept of objects, attributes for those objects, and edges or tags between the objects. So we can have an example where we have the probe IDs as being the left keys or objects, and the go IDs as being that should say right. This should say the right keys right here. Okay, I'll correct that. So the probe IDs can be the left keys, and the go IDs could be the right keys, and the edges could be the evidence codes between the probe IDs and the go IDs. Now, not all edges have to be there. And so, basically, if we take a look at this particular library, the Human Genome AV2.db, and we can form a connection to it, and that's a standard way of doing it. If I have the same name with an underscore DB connection, that forms a connection to that database. Okay, and then, for example, I can get the column names of this, and the column names for this are the probe ID, go ID, evidence, and ontology. And then I can say to table, this may take a little time, this gives the information from the right to the left and the evidence. And then I can get the left keys and the right keys. Now, I'm only doing this to illustrate that to a biologist, this is really important. You know, if you're in genomics, you've got to relate all this information. All this information is stored in these databases. Now, if you're not using R, you don't have this nice interface. Although there typically are web interfaces that are available, you know, to users of these different databases like Go and PubMed and so forth. They typically have a web interface that you can give a SQL command and get the results back. But the advantage of R is not only can I now can interface with these databases, but not only that, I bring them into R. which means I can analyze things and relate them to other statistical ideas. So it's very, very powerful to have R have the capability to hook into all these bioinformatics databases that are out there, because then I can use the full power of R using all the information, in the database. Finally, if you want to show all the links, this shows it will show all the links between, these are actually the edges between the objects on the left are the probes, the objects on the right are Go ID, and then these are the actual links. Okay. So, just one final thing. A lot of times you want to do a reverse map. In other words, instead of mapping from one thing to the other, you do actually a reverse map. And if I look at the database, I can sort of reverse map it and look at the maps going the other way, back to the symbols, which are the alphametric symbols or identifiers. By the way, and this is the final thing I will do, if I form a list, and that's the list. Okay, so I have a named list, and the names are A, B, and C, and what's in the list are W, X, and Y. I can actually reverse the names and what's in the list by using reverse map. So reverse map applied to a list, then what the objects become the names and vice versa. So that may or may not be useful, but you can do it. Okay, well, I'm going to stop here. I've actually commented out everything else. You can play with that if you want at some point, but I'm going to stop here and talk a little bit about the exam. So that's just a very brief introduction to databases and how R interfaces with them. Obviously, learning about databases is more than a half-hour lecture. This just gives you some idea of what's going on. So, let's talk about the exam for a minute. If you look at exam 1, I think you had to work, 10 out of 11 or something like that. And it will be similar, that you'll have to work. There'll be more questions, but not double. Maybe not even, it may be like 15 out of 16. There'll be a few more questions, but it won't be anywhere near double what we had for the midterm. But it will be a little bit longer. It's a 2-hour exam. So you don't forget, you can have 2 pages of notes, front and back. If you want to bring the page you already created for the first exam, you can. However, I wouldn't necessarily advise that because most of the first exam was on programming, for loops and simpler programming constructs and things of that sort. And there won't be too many questions on that. Most of the exam, at least 80%, if not more, will be on starting with S3 classes and moving forward. S3, S4 classes, creating packages, character type information in Chapter 5, for example, and then the stuff in Chapter 8. But also we had that, remember I brought in that one chapter from another book, that 9.7 on data technologies, which got into a lot of things like apply. Now there may have been something on the first exam relating to apply, but if you look at the data technologies one, there's a lot of very useful information. Where did I do that? Well, maybe if I just go down through here. If you look at the midterm exam, it was here. However, we didn't do all that much on that exam relating to object-oriented, a little bit on object-oriented programming, but not a whole lot. So the main starting point here will be with S3 class. Sort of ideas from going back into here, what are the basic ideas of object-oriented programming? And what are the models supported by R? Well, we covered 2 models supported by R, the S3 and the S4 classes. The S3 is much more informal, using generic functions, using attributes, things of that sort, whereas the S4 is a much more formal system. So you should understand the basic ideas of object-oriented programming in S4 and S3 and S4 implementations of those in R. I gave you some various examples. So if you look at S3, I gave you a t-test example as well as the linmod. And that linmod came from Frederick Leish's notes on object-oriented programming using S3. In terms of S4, I had the SNP example, the snippet notes, as well as the Leish S4 notes. Now there was some discussion on the book about S3 and S4 classes, but I didn't spend a huge amount of time on that other than some of the underlying concepts. But again, you should know how to create, in both cases, how do you create the classes, how do you create methods for them, generic functions, and so forth. Now, if you look at Chapter 4, this is input and output and R. You should look at that, but this will not be a large part of the exam, to say the least. You get into a few things. These are some, system files and file paths, and there were some basic ideas there. But I'm not going to put a lot of emphasis. That doesn't mean I don't want you to look at it, but I'm not going to put a lot of emphasis on Chapter 4. We went over that pretty quickly. Now let me indicate the following. There are some areas that, what type of questions am I going to have? Are you going to have to write a lot of R code? No. I'm not saying you don't have to write any, but it would be relatively straightforward because I can't expect you to write a lot of R code in a 2-hour exam. There will be quite a bit of R code that you either have to tell me what it does or that I actually give the output and you explain the output. So in some cases, I'll give you the R code and say, that's it, you tell me what it does. In other cases, I may give some of the output and you have to explain to me what it does. There'll be relatively little where you have to actually write the R code from scratch. There may be a few cases. But some topics are not so important that they actually require a whole question. And I'm probably going to have one or two that are true or false. So I could have a topic that doesn't warrant a whole question, may be part A of the question that's true or false. But the true-false questions, you will have to explain your answer. So I'm not giving you a 50-50 chance to guess. Some exams sort of discourage guessing by subtracting off wrong answers. A certain proportion of the wrong gets subtracted off. Some of the standardized tests do that. So you don't guess. It's better to leave it blank than guess if you have no idea. Well, at best you'll break even if you guess. At any rate, Chapter 4 is one of those chapters that deal with certain file finding things, and again, that may warrant something in a true-false question, but not a whole question. Okay, so I'm not going to be emphasizing Chapter 4. You should look at it, but don't put a lot of effort into that chapter, compared to Chapter 5, for example. So if you look at Chapter 5, I actually, broke it up into a couple pieces. Section 5.2, well, 5.1 is really nothing. 5.2 is sort of, we're looking at character data. We're looking at some various functions in or for doing character manipulation. And we have some examples from bioinformatics. So we had substrings and so forth that you should know. We had the paste, which I just used actually when I was forming a query. I did it with the paste. And how do we modify text and so forth. So some of these examples were given in the context of bioinformatics, and some of them are just fairly general. So matching strings and string manipulation. Now, in these sections, this particular first couple sections of Chapter 5, we were not dealing with regular expressions. So if you look back in the next group, where am I? Yeah, we were looking at regular expressions. We did a couple things here. So we had all these different regular expressions, and you should know the basic regular expressions. And I'm not going to give some of the hardest examples, but because some of them do get pretty hard. But you should know regular expressions. Now I went a little bit further than that with this wheat example. If you remember, I keep losing my place here. The wheat example was a really good example from the other book. If I can find it here. That might have been in this 9.8, right? No. Let's see. Is this the wheat example? I'm not sure whether it's 9.8 or 9.9. Yeah, it's in here on 9.9. So I have both 9.8 and 9.9 from the other book. And the first part of 9.9 has another example with this very long name, if you remember. And then we went into this strange data set that was it wasn't a data set, it was data given to you in a way that was very difficult. This was the original data, and then you had to make it into a data frame. And it went through a lot of operations that you had to learn. So that's a good example to study to really understand how all this works. Now remember, I also had this 9.8, which again looks at a lot of this one isn't giving results. I guess I don't have the code here. But anyway, this does if you download it, this has a lot of information relating to the apply functions and different types of more sophisticated types of operations like merging, splitting, reshaping. Those are all really, really important. So from that other book, the 9.8 and 9.9 are both important. Okay. And then we get into I think this is 9.8, I think. Yeah, this is 9.8. I've already done that. Now the matrix algebra, I'm a little undecided how much I want to do there. I'll probably have a few things just because I want you to kind of study this, but those might be part of the multiple choice questions, so they're not full questions. But you should review the matrix algebra that we covered. And then there was Chapter 8, the final 8. And that covered, that covered basically starting out in 8.1. This got into apply functions and supply functions that even went into expression set apply functions and so forth. So we did a few things that went a little bit beyond what we had done on apply before. And so that this is a fairly important section. And then the other things that we did the next thing we did was we looked at XML, and again, being able to retrieve information from XML formats, you should know the basic ideas there. So again, I may use R code and ask you, what does this R code do? And then finally today we did the database. So again, just expecting some very basics on database. So chapter 8 is a fairly important chapter. It's a jumping off point that if you want to go into this in more detail, you can, particularly in the database area and the XML. Those are two important areas, particularly the database we covered very quickly. So for the databases, just sort of the basic ideas, but it's possible I could add one question on the database. I do, that's because I actually want you to study and learn a little bit about databases. But again, the type of material I had in my file today. So that's effectively it. So let me just summarize a few things. The exam, unfortunately, is 12:17 from 7 to 9 p.m. It'll be in this room. So it'll be about a 2-hour exam. And you can bring 2 sheets of paper, front and back. By a sheet of paper, I mean 8.5 by 11. You can bring a calculator, but you can't use a cell phone to gives you a window onto the world. There'll be very little that you'll have to do by, if any computations will be very minimal, if at all. So, but if you want to bring a calculator, just in case you can, but I'm going to try to design it so it's not going to be really needed. That is, anything that you would do might be simple enough just to do by hand in terms of calculations. So, in terms of all the programming stuff we had in this first part, the types of questions I had on the first exam, as I mentioned to you, well, not, you won't need to do those. By the way, is there anyone here who hasn't picked? Several people haven't picked up their exam. Is there anyone here? If you haven't, stop in after class. I have a few. I meant to bring them today. A couple people have never picked them up. So, object-oriented programming, the main focus, object-oriented programming, S3, S4 classes. A little bit on how you create a package, which is homeworks that you just turned in. And then, in terms of the chapters, Chapter 4, Light. You might review the Chapter 3, which looks at some of the object-oriented programming. But again, most of the material there, if I give short examples, they might relate back to some of those ideas, but there are also ideas that are covered in examples. Chapter 4, Light. Chapter 5 is on text. Text processing in various ways, including regular expressions, pretty important. And Chapter 7 was creating R packages, which again, we focus more on Frederick Leach's paper for creating R packages. You can take a look at that if you want. I do want you to, those two, the DT section 9.9 and DT, that other book, these two sections are important. And in Chapter 8, the data technologies, XML, and databases. Again, that's a fairly important chapter. So that's the way I see it. If I had to guess, it might be something like work 15 out of 16, but it may be shorter than that if I give more. If I give more parts, it will be shorter. So, what questions do you have? Okay, well, you can always email if you do have questions. I was hoping to let you just fill out that SEI form, but since that doesn't seem to be available, I'll remind you by email. You should get an email once it does become available. Hopefully you can figure out what the problem is. You'll have, at any rate, in this class, you're going to have until this Friday to fill it out. But it doesn't take long, so if you get it, it's a good idea just to do it right then. So no questions? Okay, then I'll see you Tuesday a week. When did you send it?
This afternoon.
Why now?
Or this morning. It was about the exam. An idea was there was an error coming up.
You know, in terms of creating an exam or what?
In creating it, yeah.
Was that the same problem you had before?
I have no idea. I mean,
Can you talk to Mark Lilbeck? Is he in? I don't know. I haven't checked.
I haven't checked either. Yeah, I can.
Yeah,
I mean, I included him on email as well.
Yeah, there was a problem if you. There's a problem if you don't associate a question with a module. It creates a problem.
But if it's an exam, I didn't think it'd be a problem. I
You
mean,
might
I'm
want to
still
talk.
thinking-
You might want to talk to Wei Min about it too. She might be able to tell you if that's the problem.
Okay. Well, right now it's cutting off at number 31 for some reason. I don't know why.
If Mark isn't in, Mark Lilbeck can talk to Wei Min, and maybe she could tell you that. I'm not sure how you do the exams. It's been too long since I've actually used the system.
So in the S3 assignment,
Yeah.
it said you said I was missing. I'm sure you don't remember. I think I was missing the accept or reject.
Yeah,
If it was significant.
yeah, several people did.
So then that means it's going to be through the S4 assignment and the packages as well.
Yeah,
Because I used that
same.
idea.
Yeah, right.
Will that affect the grade? moving
Yeah, I
forward?
may not count on every place if that's the same.
All right,
But-
very good. All
Okay.
right, thank you.
Should work.
Wait, Dr. Han, I just want to ask you, did you say on Friday, what is the Friday, that due date for what?
Oh, that student evaluation
Ah,
it was supposed to start this morning
yeah,
and go through Friday, but for some reason
yeah.
I built them, but for some reason none of you are seeing them, so I have to go figure out what's
No,
wrong.
I mean, the due date for which homework you say?
Oh, for the homework,
Yeah.
oh, I said Friday or Saturday for the last two.
Okay,
Although I'd rather get the next to the last sooner than that.
yeah, you mean last with the R
The,
package?
the R package is the next to the last, and then that chapter 4, 5, and 8 is the last.
Okay.
Okay? So that last one you can turn in Friday or Saturday.
What about the R package?
Well, get it as soon as possible. I mean, I'll take it up till Friday or so, but
Okay.
try to get it in before then if you can.
Thank you.
But I know people have finals coming up, and
Yeah.
so,
Yeah,
you know, I'll grade it if you turn the last two in,
with, okay,
you know, by Friday or Saturday.
thank you.
Okay? Give you a little more time, because I
Yeah.
know exams are coming up.
Yeah,
Not just this one. Well, the 512, you know, these exams.
Is that like a function in R that we can use to solve equations?
Yeah, there's a function called solve.
But does it
Linear equations.
just solve the linear? I want to solve more complicated.
You mean nonlinear equations?
Yes.
Okay, well there you need to get into nonlinear methods, which it's a slightly more advanced topic. For example, nonlinear regression, if you learn how to solve those, it's a similar idea. There's a package called NL, I think, for nonlinear regression. And that gets into method. There are various iterative, you have to use iterative methods to solve
I
those.
mean, it's kind of a function, and I know there's a function called curve. We can plot the
Well,
graph.
that's plotting, yes.
But is there any something similar with that function? But we can get like we put an input x and we can get an output y, and then we can get a complicated expression.
Yeah, once you get a prediction equation, if you have a nonlinear model, you can plot it, and then once you plot it, you get an idea. You see, it's if you have a nonlinear model, it's much harder to solve,
By hand.
to estimate the parameters of the
Okay.
nonlinear model. Once you do, you can get given an x, you can predict y, just like you can with a linear model.
Okay. So
Okay, and you can graph it, and if you graph it, you often get an idea of, in other words, you typically have to start with initial values of the parameters when you're doing a nonlinear equation, and you iterate it. And so that's a much more difficult problem to do. Okay, but in R you can do all this. It's a little. Nonlinear regression is something I'm probably going to put into Stat 512 or a course like that. It's unfortunate that I don't even think nonlinear regression is covered in 545, but it should be. I've sort of complained a long time that we don't put much attention in our courses to nonlinear models, and we should put more attention. Okay.
And do you have any available time in next week?
Actually, I should stop recording.